Hello world, we're live. My name is Alan. We're doing live LeetCode practice. Chill mode today. And the problem we picked is it's one of the problems. Let me share it on the LeetCode 75 list in the category of priority queue, right? Heap priority queue. So essentially, you don't need to use the heap all the time. But let's see what we can do for this one. Maximum subsequence score. Wow, score. Let's see if we can understand it first. The name is kind of, you're given two zero-indexed integer arrays, nums1 and nums2, of equal length and a positive integer k. You must choose a subsequence of indices from nums1 of length k. For chosen indices, your score is defined as the sum of selected elements okay, from nums1 multiplied by the minimum of the selected elements for nums2. Wow. Okay, so there is some math logic here, and it can be defined simply as, okay, nums1 plus 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 multiplied by minimum of nums of selected from nums2, and you want the maximum score. The maximum score, and the values are, okay, the length is this. The values are all positive, or there could be a 0, which could, yeah, we have to avoid the 0 because you have the minimums, yeah, the minimum. We do multiply it once, but could affect the value. So the numbers are from the 10 to 5, and the length is 10 to 5, and since we can't really do, we don't want to do, we can, but we don't want to do n square. K is also okay. So this is what I understand. Let me restart the clock. Yeah, so we have some kind of indices, yeah. Some 1, 3, 5, 6, whatever, 8. And those numbers in nums1, we need to sum up, yeah, sum. And then we take those numbers, selected numbers from nums2, and then we multiply them by those. So basically we multiply them by the minimum of those. So Yeah, I mean, whatever the number is, the minimum it will be multiplied. So, so we want to find the maximum subsequence score. And we have two examples. All right, nums1, nums2, they're the same length, but the numbers could be different. Case 3, output 12. Okay, that's the index. And we want to find the maximum index. The maximum, yeah. Return the maximum possible score. That's the score, not index, that's score. A subsequence of indices is a set that can be derived from set by deleting some or no elements. Okay, so that's the score, the minimum score possible. Oh, the maximum possible score. So, I mean, yeah, we would want to take all these numbers, like, and to make the biggest sum. But if we do that, we'll need to include all of them from values for nums2, and find their minimum. So we will have to include the small ones as well, and this will be 1, like. The 4 possible subsequences are, we choose 1, 2, 3. Oh, the k is 3, so we can't use all, like all 4. We're limited with k, yeah. Yeah, so we have to choose some of the 3, and everywhere where there is 1, 1 becomes chosen. So where there isn't 1, there is 2. And we have to pick 3. Yeah, you must pick 3, all 3. So it's not like you can choose how many you need to pick. Yeah, so that's fixed. Okay, so that's good. So you might want to maximize values from both arrays, essentially. And you want to have the maximum sum, but the maximum multiplier is probably even more important. Well, it depends on what those values are in this first one. Yeah, so both are important. So you might want to just compare them, which you would do by, and k could be n. So you could get like, 100. Yeah, this number, the max. Yeah, the worst case is you have the max number. Oh, there is no option. Yeah, if you have to pick all of them, there is no option. If k is n, that's the maximum you're gonna get. You have only one variation, one subsequence. When there is smaller, then you can pick different. Okay, yeah. So we can try and go and try all the subsequences and check in once each subsequence is a linear operation. I mean, checking because the sum, you need to find the sum, you need to find the minimum. And I don't even know how many combinations you can get when you have like, it depends on the k and the n. Because if you have like three ands, I don't know, like 5 ands, 2, 3, 4, 5, and you can pick 3 different K's, and K is 3, K is 3, and yeah, 5 indices. Yeah, you can pick 1, 2, 3. For 1, you will be able to pick yeah, this, like, there will be like 3, 3, 4, 5. Then 1 will be like, oh, wait, 3, 4. Then 4, 5, and like 4. I don't know. There's like quite a few combinations. 1, 2, 4. 1, 2, 5. 1, 3. 1, 3, 4 will already be 1, 3, 5. Yeah. So there's, I don't know how many. It's hard to tell because, yeah, we have already like almost 10 combinations. 1, 3, 5. With 1 being taken, yeah, being used. I mean, yeah, 1, 2. Yeah, 1, 2. That one is used. So 1, 3, 5. Then we're gonna have this 1, 1, 4, 5 already taken. So these might be the combination just for 1, and then we're gonna have without 1, the 2, 3, 4, and so on. I'm just kind of brute force using brute force to show there is quite a few combinations to create. I can't tell right now how many. I might not need to, but what I see already, that it's too many. It's like, yeah, these subsequences is quite a lot. And that leads us to understanding that, yeah, if we have, it's not even, I don't know if it's like the worst case is even n square, because if there was like just 1, if we needed to pick 1, the subsequence of length 1, yeah, there would be n combinations. But if the subsequence is of length 2, that is already n square, because for each 1 selected, you have n more, and well, almost n other options. So, and then when you have 3, that's even more. So it's like, depending on k, the size of k, it's like just goes exponential or something. I don't know. It grows really. Yeah, it really. And so that's for 3. Yeah, for 2. Yeah, for 2, you will have like 1, 2, 1, 3, and yeah, so you'll have for 1 almost n combinations. For 2, you will have also 2, 3, 2, 4, almost, maybe half of it, but yeah, quite a lot, so quite a few. So it's much more than n square. K could be pretty big. And so this just suggests that we probably cannot afford to try all the subsequences. We want to prioritize. And the way to prioritize is to start with the bigger numbers. So if it seems like it would be more important to prioritize the multiplier. Yeah, as long as they're positive, yes, they're all positive, yes. So if we sort them, we just want to make sure we don't have a 0 in them. If we do have a 0 among them, and we could have all zeros, then yeah, let's get, okay, if we do bump into a 0, we have to jump into 0, then it doesn't matter. All the subsequences will give us 0. So then the problem is simple. But if we don't bump into a 0 in nums2, that's where that is where we want to make sure that the minimum in our subsequence, our subset, the minimum one is as big as possible. While the first one also matters. That's the thing. I mean, it could be the case that we get that when we prioritize bigger ones on the second, on nums2, yeah, it could be the case that we get when we sort them by nums2, we get zeros in the first one. Yeah. Yeah, we might have, actually it would be, yeah, it would be yeah, we might get like that. Yeah, right. So this is nums2. Yeah, we sort by the bigger ones, but they will give us a 0 on the left multiplier, because the sum of the ones of the nums1 is left multiplier. This essentially could be a 0 as well. Yeah, which would, yeah, it could be just 1. And so we do want to care about what we take from. So both are important. The right one, because it's a multiplication on both sides. Yes, yes. So we want to make the left one as big as possible. Yeah. And on the right one, on the right side, we want to avoid the small ones. Yeah. It looks like we have the same priority for both of them. We want to avoid the smaller ones on both sides. The smaller ones. And how do we do that? So it's kind of a trade-off. I mean, if that's the case, yeah, we're gonna get those. If it depends on what the k is, but if the k is 2, I mean, it doesn't matter. Yeah, whatever we pick, it's gonna be. Yeah, the opposing number is 0. So, oh, not. We need to. Yeah, if the k is 2, we definitely want to exclude the zeros. So yeah, but we can't get anything out of that. So in this case, yeah, if the k is 3, we'll hit the zeros anyway. So if k is 2 and we have 1, then we should take like, we'll include this. That will give us 1, and that will give us 1 on. Yeah. Yeah, we'll go for these. Yeah, these 3. Interesting. Let's try to simplify this. Choosing index 2. Yeah, by the way, example 2, k is 1. So it's kind of a simple case. We'll choose index 2. Oh, that's index 2, 3 and 10. And they will be multiplied. That's our maximum score. What if we do it like that? Like we start with one index and find the index that gives us the maximum score by 1. That's not the worst approach. Let's see. Yeah, so if we go over to arrays, that's n squared, because k could be almost as big as n, and that's kind of n squarish. So if we'll try to build to catch each index, and for each index recalculate the score for each additional index. Like, but the logic is not that bad initially. Yeah, we find, let's say we find that the answer could it start with index 2? Okay, because with index 2, we have 30. Now we go for the second. Let's say we need to, we will go again and look for all the other. Look at all the other options. Find the one that has, let's say, maximum at nums2. Yeah, for k equals 1, answer is this. For k equals 2, once we have that, let's say we start with 2, then we go over the rest of the list and find the biggest score for this separate index. Wouldn't that be the best combination? So the rest that's left would be the rest that is left. So we'll be like so that's 28. Then the first one. The first one, I mean the 0 one, So what will it look like? That would be 4 plus 3 multiplied by minimum one of them is 7. So that would be 7 by 7, 49. 49. But we have an interesting other option. What if we look if we look at this one? Oops. This one gives the biggest 49, but this one gives the biggest multiplier for so 3 plus 1 is 4. So if we multiply 4 by 9 is 36. No, it's not. It's not going to be. It's going to be smaller than that. So this number is good with this puffing up the first number, but this one is really small. So is the math right? Because this multiplier will apply for both. Essentially, it will apply on both the 4 and the 3 that we had initially, and the 4. Because what we initially found was this 3 by 10. Now we found 3 by 10. We thought, okay, 3 by 10 is top score. Then we say, okay, 4 by 7 is top score of the rest. 7 is going to be less than 10, but it really depends on what that was, because if that was like that 3, three plus 1 or 3 plus 4, yeah, this drop, if that was like 30, okay, then then multiplying, well, that will be, oh, the other that 4, 7 will still win as a separate in a separate competition, but 30 will be really good with 9. So yeah, because you have that, but oops. But if we compare 30 plus 1 with 9, then 9, that's much more. So we can't do separate evaluations and just find the ones like, yeah, because this multiplier on both ends, each part of the sum is important. And the bigger multiplier, yes, some multipliers might have a very small, they might be big, but they might might have a very small respecting number in the nums 1, like this 9 has. And that breaks, that kind of confuses us. Okay, what's the timing? It's 32 minutes. We're looking for the logic. So selecting, so we need to, for each combination, so I was trying to find, okay, to see if we can look for the next index by just counting its score separately. No, we can't do that. We need to count the score together with the one that we have already. And that's fine, we can do that. We can count the score with the one that we have already. That will, in that case, we'll just need to find, okay, we'll have a list from the nums 2, so that's iterative to find the minimum. Or we'll keep the priority queue, so we'll know the minimum ones all the time. And if we keep that, so it could be more effective than that. And the second one, calculating the sum for the numbers from the first one is just adding the numbers. So it's simple. So basically, we will need to recalculate the score k times Like we found one score here, then we'll go over the rest, finding the second score and recalculate score every time on every step. That's n times. Then if the case 3, then the third time we need to recalculate it again for each remaining option. And this score recalculation in itself could be log n. Yeah, I guess if we use a effective priority queue. Yeah, so two sub-problems. Calc score, compute score, and then but then iterating over the k could be pretty big, and that will create a lot of like when we find the biggest score for K2, then eight. By the way, it's not gonna jump. Like in this example, in this first example, if we try that, if we try that logic, because for K1, the answer will be 2. It will be 3 by 3, which is 9. K2 will, the biggest one will be 2 and 4. But we need to calculate together. So we'll try so what are the options? Yeah, we'll try with 1. Yeah, we'll have like 2 and 1. 2 and 0 first. That will be 3. That 3 plus 1 by 3 plus 2, which is 4 by 5, which is 20. Oh, wait a second, not plus. We need to find, we get the minimum, so that the minimum will be 4 by 2, which is 8. Yeah, I forgot then then we need to start like this one. The minimum, okay, 1 is 3 plus 3. The minimum is 1, so which is 6. And then it's gonna be 3 plus 2. And of these 2, the minimum is 3. 3. So that's 5 by 3, which is 15. And by the way, this is bigger than if we choose 3. So we actually add a k, but we get a smaller number. So let's say we picked this one. Then we, here is the deal. You see, this right side is kind of tricky because what matters is the smallest one. All the other ones don't matter anymore, how big they are. They just matter as hopefully they're not smaller. Okay, but they could be the same. Or they could be much bigger, but that doesn't matter. So it doesn't matter how bigger they are. Now, what matters is that they give us the biggest left hand. Jeez, that's a tricky problem. 40 minutes. So priority. So their priority stops on the left side. You want to have them as big as possible. On the right side, the size matters only as for the smaller one, the smallest one. How big the other ones doesn't matter, as long as they're bigger than it. But the smallest one, yeah. That's the size that matters. Interesting. So, and yeah, it's obvious brute force is not really an option. But even with this approach, I mean, there is this problem of calculating. Yeah, but if we go like with this back to this algorithm, yeah, if we go like, okay, we think that 2 and 1 is the answer. Yeah, we'll need to count the rest. We think that 2 and 1 is the answer. Now for K3, if we take 2 and 1, and then we'll just try with the 0. Yeah, and we'll basically have how many more? We have 2 and 1. We have 2 more options to try with the with the 0 and with the 3. So with the 0 and with the 3. So with the 0, it will be 0, 1, 2. So what will be 1 plus 3 plus 3. And that will be multiplied by 2, which is the smallest one. Oh no, it will be multiplied by 1. Yeah, so that is 7. And this option will give us, yeah, we'll avoid, I guess in this one we'll avoid 1. So that will be like 1, 2, 3. That will be 3, 3, 3 plus 3 plus 2. multiplied 1, 2, 3. Wait a second. How come there is 1? Oh, there you go. There you go. So this one, oh no, wait a second. It's not 2, 1. 2, 1 we have tried. Jeez. Sorry, that's wrong. So we tried 2, 1, 3 plus 3. And so there is, outside of 2, there is 2, 3. Yeah. So 2, 3 is it's 2, 3. 2, 3. Yeah. Now, yeah, so that's 2, 3, 0. That will be and 2, 3, 1, yeah, essentially. So that will be 1 plus 2 plus 3 multiplied by 2, 2, 3, 0. Yeah, multiplied by 2. That is 6. 2, that is 12. Yeah. And this one gives us 2, 3, 1. This one is 2 by 3 plus 3. Multiply 1. So that is 8. So in this instance, we did come. This path did bring us to the right answer eventually, but I'm not sure. I'm not convinced that it's going to do that in all different cases. That the previous two, if the previous two gave us the biggest answer, that means that the multiplier they produced on this from nums2 was better than all others. Because we definitely don't want to stay away from small multipliers. Kind of easy on the right side. Okay, let's play with sorting. What if we sort these? Essentially we'll have, give me the maximum number from the nums2. Okay, we do that. And then we'll take the corresponding number from nums1. And that, as we know, will not bring us the biggest single. Yeah. This problem seems a bit too confusing, at least at this moment. I think So we tried several ideas. Building that subsequence one by one by iterating and recalculating score. This might be the path. Could we implement it efficiently? If we could we implement it efficiently? It's kind of the question. I mean, it's still gonna be k(n) squared, because, or should we say k square? Yeah, it's gonna be k squared, because for each k we'll need to check all the rest. About k squared, yeah, all the remaining, which is about n squared. Which could be, in the worst case. So we can't really do that, right? Yeah, we have like almost 1 million n, and I don't know, half of the k's, and for each k, while we're doing that, we'll need to go over the rest. Actually, we need to go over the rest of n. So it's like k times we'll iterate n, essentially. And that's pretty much n squared, yeah. So there's probably a more interesting solution here. More interesting. What if we take like the kth smallest number from if we kth smallest number from nums2, which is like 2, so if we take that kth smallest number, by the way, we did solve a problem like that. Kth largest element in an array. Oh yeah, actually that's what I meant. Kth largest, yeah. We'll solve this one. Kth largest. And we did that using counting sort. Kth largest, yeah. We could do counting sort here because the range of nums is 10 to 5. If we need to or just sort them. It's okay. We could just sort them. Anyways, we're reaching the hour, and I'm I'm still trying to find the solution here. Total score cost to hire K workers. I mean, I understand the heap. I understand sorting. I don't see how to do it. Like what exactly to do to use that and get it done. If this works, it's still too much. Yeah, so we can't try all the options. We can't like there could be too many options to try. Because for each K, you will need to try all the ends left, all the nums left minus K. So not really viable. I don't, yeah, this and that is like 10 to 10. That's 10 to 10. That's too much. So I'm thinking I should take a break here. It's I'm nearing. We're about, yeah. We're pretty much. We're reaching our time. It's reaching our hour, but it's probably a good exercise though, because yeah, we kind of played with the different. Yeah, and we know we need to find a different approach. Yeah, not this n squarish one. Something better. Some idea for the second index that doesn't come from either checking all of them. It comes from some priority. So we could like sort them initially and then get that. Yeah. They could be zeros. Yeah. So we'll need to return a zero. But in the other cases, yeah, we'll need to stick with those non-zeros on the right side. And the simple case would be if they actually if they both are increasing in the same. If they're both increasing, then it's obvious that the biggest indices are the ones to go with, because they're both will give us the biggest multiplier in both ends, on the left and the right. If they were both increasing. That's an interesting simplification. We'll think about it. Anyways, that's our hour. We'll maybe try that problem a bit later. Thank you for watching, and we'll see you in the next video.